Some fractions that we need to integrate can be quite straightforward. This is the group that will integrate to ln f of x. Now, how to spot them? So the top of your fraction will be the differentiated version of the bottom. The posh term for this is that the top is the derivative of the bottom, so you might come across that language. This will be easier for you to understand if I do a couple of examples. So here in example 1, let's have a look at the bottom of this fraction and differentiate it so you can see what we're talking about. So x cubed becomes 3x squared, and minus 2x squared, we're going to multiply by the 2, so we'll get minus 4x, and the 6 disappears. So you can see that the top is exactly what you get when you differentiate the bottom. So what that means is that when we integrate all of this, which I'm not going to write out again with respect to x, we're going to get ln of the function of x that's on the bottom inside modulus signs. So don't worry too much about that. That just means that whatever this works out to be, you want to make it the positive version of it. And of course, don't forget that you always need to add c if you don't have limits to work with. So let's try another example with a slightly more complicated twist to it. So in this case, we've got sec squared 3x over tan 3x minus 2. So let's think about differentiating the bottom there. So tan 3x differentiated, if you use your formula sheet, becomes 3 sec squared 3x. And of course the minus 2 will just disappear. So our top isn't an exact replica of the differentiated version of the bottom. So what we're going to do in order to make it work is we're going to rewrite it as 1/3 in brackets 3 sec squared 3x over tan 3x minus 2. So you can see what I've done. To get that 3 sec squared 3x on the top, I've put the third outside to counterbalance that. So now when we do the integration, we're going to end up with a third ln of the bottom in modulus signs, so tan 3x minus 2 plus the c, of course.